Hello everyone, welcome to the Week 9 lecture, lecture video for COMP3141, Software System Design and Implementation. So this lecture, we're going to be talking about some theoretical topics that relate to type systems. So far we've already seen Haskell's type system being used to enforce various invariants and other properties that we wish to enforce statically, that is, without running the program. And now we're going to look a little bit more into the details of how type systems are constructed and what makes type systems special when it comes to ensuring properties about our programs. Also, we'll look into some deep theoretical results that connect type systems and formal logic together in a very intimate way, such that really we can't make a distinction between a type system and a logic. So we'll get into that. But in order to get into that, I need to sort of go over some discrete mathematics that maybe some of you don't remember, or in particular, if you did only Math 1081 at this university, then I suggest that maybe the way they teach logic in that course is not really appropriate for what we're trying to do. So what I'm going to do is go over the system of presenting logic called natural deduction, which you may have seen if you've done certain other courses. In particular, I'm thinking of COMP3141, or certain mathematics courses, or my COMP3161 course, all of which use natural deduction. But if you haven't done any of those courses, that's fine. We'll go over it today. And it's a fairly intuitive way of presenting formal logic. So if you've seen logic before, and I hope most of you have, then this shouldn't be too much trouble for you. So, what is natural deduction? Well, it's a way of specifying a logic, and a logic is just a system of mathematical reasoning by which we can deduce theorems from axioms. So I used a lot of terminology there. A theorem is a proof, or is a proved logical statement, or in other words, a proved sentence, and a proof is a application of logical rules that show that the proof follows from the axioms, which are the basic sets of facts that we have in our logic. So the easiest way to specify a logic, in my opinion, is with a system called natural deduction, and in that you just give a sequence of rules, one for each of the connectives in the logic. So for example, propositional logic, our normal logic, just has and, or, so conjunction and disjunction, implication, which is A implies B, the arrow, or negation, right? And we have true and false as some constants. And those connectives and constants each have introduction and elimination rules. So an introduction rule tells me how to prove a particular connective. So for example, in order to prove the conjunction of A and B, I must provide a proof of A and a proof of B. That's an example of an informal way of describing the introduction rule for conjunction. And the way we describe introduction rules in natural deduction is with this notation here. So this notation you may have seen before. Essentially, it looks like a fraction, but it's not a fraction. All it's saying is, in order to show the thing on the bottom of the horizontal line, I need to show the thing on the top. And what does this thing on the bottom and the thing on the top say? Well, it says this turnstile symbol means that you can prove the thing on the right under the assumption of the things on the left. So, implication, in order to prove A implies B, that's what that's saying, then we need to add to our set of assumptions, which we've just called gamma here, an extra assumption A, and then if adding that extra assumption A, I can prove that B holds somehow, then I can show that A implies B, just with the assumptions gamma. So this is the introduction rule for implication. It's saying that in order to prove an implication, you first assume what the implication assumes, and then show the conclusion of the implication under that assumption. That's what that's saying. So this notation may be a bit unfamiliar to you, but I'll show you later on exactly why we have it this way. It makes certain proofs very clear. Okay, so let's keep going. Let's look at the elimination rules. So introduction rules tell me how to prove a particular connective or constant. So in order to prove implication, this is how. But what elimination rules let you do is if you already know, say A implies B, then what can you conclude from that, right? So it's the dual of the introduction rule. So where the introduction rule is saying, here's how you prove it, here's how you establish that the connective holds, the elimination is saying that if you know that the connective holds, here's what you can do with it, right? So we have an elimination rule for implication says that, well, if you already know that A implies B, then if you also know A, you can just conclude B, right? So this is if you have two judgments on the top of these this horizontal line, that's saying that you need to prove both of these things in order to prove the thing on the bottom. So we say if you can prove A implies B from your assumptions, and you can prove A from your assumptions, then you can just prove B from your assumptions. You don't need the A implies anymore, right? And this rule is called modus ponens, modus ponens in proper Latin pronunciation. And this rule is one of the few with a Latin name. There's a couple of others as well. And some of you may have heard of that name before. I'm pretty sure it's actually used in discrete maths. There's also introduction and elimination rules for conjunction, for example. So as I said before, in order to prove A and B, we must prove A and we must prove B, right? So if I have a proof of these two propositions independently, then I have a proof of their conjunction. So far, so good, I hope. Now, if I know A and B, there's two facts I can conclude from that, right? I can conclude that A is true, and I can conclude that B is true. So that's quite nice. And if we try to come up with the rules for disjunction, that is OR, then we're going to get something quite similar for the introduction rules for OR. The introduction rules would say, if I know A, then I can conclude A or B. So it's like we flip these rules upside down. And similarly, another introduction rule for disjunction would be, if I know B, then I know A or B. But the elimination rule for disjunction is a bit strange. I can't just take this introduction rule and flip it around. That would say, if I know A or B, then I have two things on the bottom of this rule. That doesn't make any sense. So the way we eliminate disjunction is a little bit strange. If I know A or B, there's nothing I can immediately conclude from that. Just knowing A or B, I can't conclude A because it may be B that's true, not A. And similarly, I can't conclude B because it may be A that's true, not B. And I don't know which of A or B is true if I know A or B. So what we do is we say, so if I know A or B, then if assuming A, I could show P, and assuming B, I could also show P, then we know that regardless of whichever A or B it is, we know P is true. So therefore, I can conclude if I know A or B, and I can prove that A implies, or A entails P, and B also entails P, then that means that no matter which of the two it is here, I can conclude P is true. And that's how we discuss elimination for disjunction, right? So we have this extra assumption P here, and this P could just be anything. Okay, and the introduction rules are, as I said, just the elimination rules for AND flipped around, because if I know A, then I know A or B is true, trivially, and if I know B then A or B is true, similarly. Now for true and false, we have one introduction rule for true, which says that you can always prove true. And when I have nothing above the line here, that indicates that you don't need to prove anything in order to prove that true is true. You just automatically know that as a fact. So this is an example of an axiom. And false is something that you can never prove, right? So there is no introduction rule for false. There is, however, an elimination rule for false. And what it says is, if you can prove false, then you can prove anything. So, what? This seems a bit strange to some people. Why is it that you can prove anything assuming false? Well, there's a few different ways to think about this. One would be if you said something like, if I have some false proposition, like I have $1 billion, that's not true. But if I said, so if I'm in a world where I have $1 billion, then I could conclude anything, because there's no way that I could be in that world where I have $1 billion, and therefore there's no way to invalidate my proof of this fact. Another way to think about it, which is a bit more of a constructive way to think about it, is if I can say, if I can prove false, then that means false is true. So that means everything is at least as true as false, right? And so if false is true, that means everything is true, right? So this ex falso quod libet rule is a little bit confusing sometimes for people, but essentially what we're saying here is that if you can show that your assumptions do not make sense, that there's a contradiction in your assumptions, then that means that the world that you're trying to discuss does not exist. And therefore, you can make any statement about it, because you're always making a statement about the worlds in question. And if there are no such worlds, then any proposition holds. So there's a few different ways to think about this. Whichever one makes the most sense to you. Another way to think about it is if you think about implication. If we know A implies B, in our if you remember from discrete maths, we can translate A implies B into not A or B, right? And so if I have false implies P, then that changes to not false or P. And not false is true, which means this is always the case. And so therefore, not false or P is a valid proposition. So that if you think of this horizontal line as an implication sign, that also works out. Okay. Anyway, so these are the rules that we have for logic, specified in the form of these rules. So why did I specify them in this way? Well, we're going to do some proofs now. I'm going to prove some logical propositions, and I'm going to do it by using these rules directly. And then you'll see, hopefully, why I did it this way. Okay, so A and B implies B and A is the first proof we're going to do. And I have prepared on my paper here all of the rules that we want to use. So let's do the proof. We're going to do A and B implies B and A. And we're doing this under the assumption of nothing, right? We are not proving this under any particular assumptions. So our set of assumptions gamma here is empty. Okay. So now I need to play the video game of proof, which is I need to find the tool in my toolbox, which I've collected all the way on this left-hand side here, that will apply to my current goal, right? So what we do is we look at the symbol on the topmost part of the formula tree. So the invisible brackets here in the formula are like this. So that means that the topmost connective that I'm using here is implication. So when we have a topmost connective like this, we typically want to prove it using the introduction rule for that connective. So in order to prove an implication, I want to use the introduction rule for implication, introduction, and I'll write it here, implies introduce, and the thing that rule requires me to prove is we take the antecedent of the implication and we add it to our set of assumptions, which was previously empty, so that's the only assumption that I need. And now I want to prove the right-hand side of the implication, the succedent of the implication, which is B and A. Okay, so that's using the implication introduction rule. And now I have a look at my topmost connective and I see that it's AND. So I'm going to use AND introduction. Okay, now in AND introduction I have two possible things that I have to prove. I have to show firstly that A and B entails A, and also that A and B entails B. Okay, so now I've run out of introduction rules to use, so now I'll probably get started using some elimination rules. If I look at my set of rules here, I do have these two rules and elimination, and seeing as I do know a conjunction here, an AND, I can use those rules. So let's use here, oops, wrong color, here and here, we're going to use two different elimination rules. Here I'm going to use and eliminate 1, and here I'm going to use and eliminate 2. And this will give rise to A and B is still my set of assumptions. Gamma is still the same on both sides. But the thing I have to prove here for AND eliminate 1, it allows me to add a conjunction on the right-hand side. So we'll add that. And I'm going to choose B for B here, so I get A and B. And here also I'm going to do the same, A and B. And this gives me two entailments that look like this. P entails P, which is trivially true, right? We say that whenever you have P entails P, that's trivially satisfied. So we can finish our proof this way. And then what we've done here is show that our original proof is through successive application of these rules, reducible down to something that is trivially provable, i.e. self-entailment. So this is one way to prove logical statements. So another way to write this tree, if we don't want to keep writing A and B, and all of our previous assumptions in the set gamma, what we can do instead is just annotate whenever we introduce a new assumption into our set. So here, implication introduction introduces a new assumption, and I'll call that assumption alpha. And then whenever you use that assumption, i.e. here and here, you annotate the rule where you use it. And this way, you don't actually you can get away without writing out all of the assumptions on each of the goals. So the way we would write this tree in this alternative presentation would be A and B implies B and A, we're going to use implication introduction, and we'll call the assumption alpha. And now I need to show B and A. And I don't bother showing the assumptions on each line. And then I'm going to use conjunction introduction, and I need to show A and I need to show B. There I use conjunction elimination 1, and I need to show A and B, which is the assumption alpha. Here I use conjunction elimination 2, and I need to show A and B, which is the assumption alpha. Right? So this is a slightly shorthand way of writing the same tree, and it's a bit easier to read sometimes because we don't keep having to write this turnstile and all that. Okay, so now let's do another example. And in this other example, we want to show A or false implies A. And this makes sense, right? We know that A or false, anything or false is equivalent to just that thing. So A or false implies A. We do know this is true, but let's actually prove it using our natural deduction system. A or false implies A. So the top level connective here is that the invisible brackets, once again, are here. So the top level connective is this arrow. So we'll use implication introduction, and we'll introduce our assumption as alpha. Now, so now what I need to show is A. Ooh, why is that happening? A. There we go. So now how do I show A? Well, the assumption that I have is A or false. So in order to use an OR, I need to use the elimination rule for OR. And the thing that I want to show is A. So my P, in this case, is going to be A. And the A or B here is A or false. So the substitution here is P is A is A, and B is false. Right? This is the substitution we're applying to the rule OR elimination. So I'm going to use OR elimination here. And the two assumptions that I'm going to introduce, the assumption in this rule and the assumption in this rule, I'll call beta 1 and beta 2. Right? So I'm not writing them out in the entailment relation because it's a bit too long. Instead, I'm just giving them names, and we'll see how this works. So I need to show A or false, and I also need to show A, assuming the assumption A, and false. Sorry, also A, assuming the assumption false. Right, so in each of these two cases, I have two different assumptions. Here I have the assumption A, and here I have the assumption false. Okay, hopefully this makes sense. So firstly, in order to show A or false, we use the assumption alpha that we introduced here. Okay, and then in order to show A, I use the assumption beta 1. Because beta 1, let's write out what the assumptions are. Alpha is A or false. Beta 1 is A, and beta 2 is false, right? So these are the assumptions that we're making, and beta 1 is in scope here. This is the scope of beta 1, and this one is the scope of beta 2, right? Okay, so in order to show A, I can just use beta 1 here because it's beta 1 is A. And then in order to show A here, I need to use my other assumption, beta 2. And beta 2 says false. So how do I do that? Well, I need to use my ex falso quodlibet principle, which is also called false elimination. So we'll use false elimination, and now I need to write, I need to prove false instead of A, and the way I prove false is with my assumption beta 2. Okay? So what we can do, just to make this extra clear, if it's hard to follow where all of these assumptions are coming from, if we write this out with the entailment relation, just one last time so that it's clear what's going on, we have no assumptions here. After we apply the first rule, implication introduction, we introduce the assumption A or false, and we need to show A. Right here I left it out, but here we have the assumption A or false, which we called alpha. Then I applied OR elimination, and I needed to show A or false entails A or false, which is trivially true. And I needed to show A or false and A entail A, which is also trivially true because A entails A. And I needed to show, I'm running out of room here, A or false. Actually, let me write it out more clearly. I will just extend that line. I need to show A or false. False entails A. In order to show that, I used false elimination, and then I needed to show false, assuming A or false, and false entails false, and we're done, right? So this is the full version of the tree, which includes the entailment relation, and here I left it out because it's a bit easier to write. Okay, so that's our proofs. So now let's think about how we would go about proving some other connectives. So you'll notice I introduced AND, I introduced OR, I introduced implication and true and false, but I never actually introduced negation. So what would negation be equivalent to? Well, we have this well-known identity that A implies B is the same as not A or B. We also know that A or false is the same thing as A. So that means that if I said A implies false, that's the same thing as not A or false, which is the same thing as not A. So therefore, negation is just the same thing as implying false. It's the same thing. So we'll just define not A to be the same thing as A implies false, right? And that way we don't need to have special introduction or elimination rules for negation. Instead, we just use the same elimination and introduction rules as implication. Okay, so let's do an example. We'll prove A implies not A. Okay, let me go over to the board again. So I want to show that A implies not A, which is A implies false, implies false. This is what I want to show. A implies false, implies false, under the assumption of A, or rather, yeah, implication of A. Okay, so let's try to prove this, and the brackets are like this. Well, we have to use implication introduction. So let's do it with the entailment relation just to make it extra clear. But there's many, we could go without, but I might want to do it in this case. So now we are assuming A, and we want to show A implies false, implies false. Okay, well, we've still got another introduction rule we can use. We use the introduction for implication there, and now we want to use it here on this implication. So let's use it again. And this time we have another assumption. So we have A, and we also have A implies false. And we want to show false. Okay, well now I'm out of introduction rules. Remember, we have no introduction rule for false because we can never prove false just without any assumptions. So we're going to have to eliminate something. So the only connective that I have in my set of assumptions here that I could eliminate is an implication. I have this A implies false here. So let's try to eliminate that. We'll use implication elimination, the modus ponens rule. And that means I need to show an implication. The implication I'm going to try to show here is A implies false, because that's the same thing as my assumption. So let's put in our assumptions just to make it clear. Oops. A implies false. And then I need to show the left-hand side of that implication. So I'll once again still have all my assumptions. A implies false. And I need to show A. Okay. Well, A implies false is one of our assumptions, so this rule is done. And A is also one of our assumptions, so this one's done. So that means overall, we've now completed the proof that A implies not A, right? Which is this expression here. Cool. So we've seen how to deal with negations now. Go back to the slides. Let's try to prove the opposite direction. Now some of you may be seeing where I'm going with this. We may actually encounter a problem here. So don't be surprised if we get stuck. So let's see. So what we want to show now is the opposite direction of what we just showed. So we want to show that if A implies false, then that's the same. Well, then I can conclude A. Okay, turnstile. I want to show A implies false, implies A. If I use my implication introduction rule, which is the only introduction rule I could possibly use, then I get on the left-hand side of my turnstile a large assumption, A implies false, and I need to show A. Oops. Well, here's a problem. I can't use any of these. Let's go through all our rules and see if we could use any of them, right? So for all the introduction rules, they require me to have a connective or a constant on as one of the conclusions. And the conclusion I'm trying to show here is just A, so there's no connective or constant there. So we can rule out our introduction rules. None of them will possibly work here. Okay, so then looking at our elimination rules, we can only use the elimination rules that work on an assumption that we actually have. So we can't use OR elimination, for example, because there is no OR assumption. The only assumption we have is this implication thing. So we can't use OR elimination. And we can't use false elimination. There's no false here. There's just this big implication. So the only thing we could possibly use, can't use AND elimination either. The only thing we could possibly use is implication elimination, the modus ponens rule. So if I try to use the implication elimination rule, then I need to show an implication. The only implication that I have is A implies false. The only implication I could possibly use is that same assumption. So let's do that. So that part is easy, but now I need to provide a proof assuming A implies false, I need to provide a proof of A implies false. This seems a little bit strange. Let me just double check that I got that right. I think I did, yeah. Well, we can keep going and see what happens. The only rule I can use here, so this was, the only rule I can use here applies to this arrow. So let's use implication introduction again. Now I have an additional assumption, so I have still got my old one, A implies false, and I also have the assumption A, which I introduce here, and I need to conclude false. There's no introduction rule for false, so once again, the only thing I could possibly do is apply implication elimination to that same assumption that I just did. But then we're just going to go around in circles. We would once again have to prove A, and we just do not have a proof of A. So no matter how many times I keep applying this implication elimination rule to this assumption, we're not going to get anywhere closer to actually getting a proof. We just keep growing this tree higher and higher and higher. And in fact, it is in this statement that we know to be correct from our logic previously, but perhaps in Math 1081, is not even provable using any of these rules. It just doesn't work. So let's draw a sad face here. So why doesn't it work? This is an interesting problem, and it has philosophical as well as practical implications. Some of you may have heard of the difference between constructive logic or intuitionistic logic and classical logic. So in your logic classes that you've done so far, most of you probably would have only seen classical logic. Classical logic admits this certain extra principle that we don't currently have. Classical logic says that for any proposition P, either P is true or P is not true, right? Another way of saying this is, if we know that not A is the case, then we can conclude A. In fact, this exact assumption that we were trying to prove. These two things are equivalent, right? You can prove that one implies the other, but they are not provable from the set of rules that we have here. This rule is called the law of the excluded middle. So why do we care about this? Well, constructive logics, which is the logic that I've specified here today, do not allow us to do a proof by contradiction. So for example, if you think about a proof by contradiction, such as you have seen in mathematics or in other computer science courses, a proof by contradiction works by saying, okay, well, let's say the thing I'm trying to prove is false. If that's the case, then I can show that that is not the case, that it doesn't make sense. In other words, you show that if the thing I prove is false, I can derive a contradiction. So in other words, you're saying, assuming not P, I will show false, which is the same thing as not P. So if you prove a property by contradiction, you're assuming that not P is the same thing as P. But why would we want to make a distinction between something being not true and something being true, right? Something proven to not hold and something being proven to hold. Well, this distinction allows us to make a difference when it comes to things like existence proofs. In classical logic, if I prove that something exists, then it suffices for me to prove that it is impossible for it not to exist. I don't actually have to say what it is. In a constructive logic, I need to provide the thing that I'm saying exists. So for example, if I say there exists a number that satisfies certain properties, blah, 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 then in a constructive logic setting, I need to be able to write down what that number is. In classical logic setting, it just suffices to say, well, if this number didn't exist, then we would end up with a contradiction, right? And this is a somewhat less satisfying proof. The reason we care about this is, in computer science, we like algorithms. We like our properties to be computable. So in a constructive logic, every proposition that you define, you can, well, it's not necessarily decidable whether or not the property is true, but if you have a proof of the existence of something, that means you have an algorithm to compute what that thing is. So there's a philosophical argument here, which is that something being proven to be true is not the same thing as it being proven to be not false. And that's the philosophical argument, but the practical argument is that we want our proofs of existence to contain content, to contain some sort of algorithm to provide the thing that we're saying exists. So that's a recap of logic. So I've introduced all of the different connectives that we're going to use and talked a little bit about the difference between constructive and classical logic. So now we're going to actually get into the theory of types that I said I'd get into 40 minutes ago. So what we're going to do is we're going to take Haskell and we're going to throw away almost all of it and just leave behind the very smallest possible programming language we can. These concepts apply to any programming language to a greater or lesser degree. However, for the purposes of demonstration and for the purposes of this lecture, we don't want to deal with a complete language like Haskell. Instead, we just want to deal with a language that is that I can fit all on one slide, right? So what we're going to do is take Haskell and get rid of a lot of stuff. We're going to get rid of all of our user-defined types. Instead, we're just going to add in a set of built-in types, which we can use to express all of the things we want to express. We're going to get rid of polymorphism. We might talk a bit about how polymorphism works again later on. And in order to define functions and bind variables, we'll just use lambda. So we won't even have let. Instead of let, you can just define a lambda and then immediately apply it to an argument. And we won't have equations to define functions. We'll just define functions with lambda. Okay? And this is essentially Haskell without most of its features. And this language is called the simply typed lambda calculus. And this was invented in the 40s by Alonzo Church as a model for logical systems and a model of computation. So our small set of types here that we're going to introduce will be enough to express most of the data that we normally use in Haskell, with a few exceptions that I'll get into later on. And so we can argue that what we're doing here is really just describing core Haskell. It's Haskell without any of the syntactic sugar, but it still has all of the fundamental concepts that make Haskell Haskell, and therefore when we talk about properties of its type system, we can apply those properties to Haskell as well. So what we're going to do is use these same logical inference rules that I just used for describing logic to describe how we give types to various expressions in our language, in our minimal Haskell, our simply typed lambda calculus. So, firstly, we'll talk about lambda expressions. If I have a lambda expression, if I say lambda x e, so \x arrow e in Haskell, then that is of type a function from a to b, right? That is a function from a to b if assuming that the variable x is of type A, then the expression e can be shown to be of type B. Right? So I have a rule here that's describing how I can give a type to an expression. So I have this expression here, lambda xe. It's a function that, given an a, if x is of type A and then e is of type B, then lambda x dot e is of type A implies B. That's what this rule is saying. So this is like the introduction rule for a logical connective. Here, what we're doing is talking about how we give a type to a particular form of expression. And for function application, if I have a function application, E1 is my function. So if E1 is a function from A to B, and E2 is an argument to that function of type A, then I can apply that function to that argument, and I will get a result of type B. So that's how we type lambda expressions and function application. But what other types would we need other than just functions? Well, we have some fundamental data in many programming languages like ints and bools and stuff, but in our language here, we want to really boil things down to their smallest possible components. So in addition to our fundamental building blocks, we normally have some way in most programming languages to take 2 bits of data and combine them into one type, right? So for example, in Haskell, the simplest possible example I can think of is a tuple, right? We have a tuple of A and B. Then that means I have a value of type A and I have a value of type B, and I can put them together into one value, a tuple of A and B. So almost all languages have ways to do this: tuples, structs, records, whatever, even classes if you want to include object-oriented languages here. And there's also another axis of composition here. In addition to like composing these things together such that you have both of them, you can also compose things together such that you have one of them, and like a union, or an either type in Haskell, or one of those. Whenever we have a data declaration in Haskell and we use the vertical bar character, we say maybe A, for example, is a just A, or it's nothing, right? That or notion is this other notion of composition where we can take the union of 2 types. So firstly, we're going to look at conjunctively combining values, that is, taking 2 values and putting them into one value, such as with a tuple. So you do that with a tuple in Haskell. Take 2 float values and we combine them into one using tuples. You can also use a record or a data type here to do that if you really wanted to, but for a point it's probably a bit overkill. You can do the same thing in C with a struct, right? We can combine a C structs together, two C types together using a struct, and this gives you both of the values. In Java, you can do the same thing with a class, although supposedly you're supposed to write it like this for some reason with a whole pile of getter and setter methods. This is really just an infelicity in Java's design and nothing really fundamental. So what we're going to do to add this notion to our minimal lambda calculus language is just use tuples. And specifically, we'll only use tuples of 2 elements. So we have A and B. We don't have type declarations, data, or anything like that. We don't have named fields like records. You can just get away with having tuples. And if you want more than 2 values to be combined into one, then you can use more than one tuple, right? So you just have int and a tuple of int and a tuple of internet, right? To have 3 integers. So how do we construct a tuple? Well, we just put the 2 expressions for the left and the right-hand side in brackets, right? So if I have a tuple here of E1 and E2, that is of type a tuple of A and B, if E1 is of type A and E2 is of type B. That's what this is saying here, right? If I have E1 of type A and E2 of type B, then if I put them together in a tuple, the result is of a tuple type. And then if I apply first to a tuple of A and B, then I get A. And if I apply second to a tuple of A and B, then I get B. So some of you may have already noticed that these rules look a little bit familiar, and we'll come to why that is in a moment. But first I want to introduce a few more building blocks to our types. So we've got ways to combine values now into tuples, and we'll also need at least a type for like a fundamental type. Like we can currently combine two types, but we can't even create a type to combine in the first place. So let's add a unit type. So we've got the unit type in Haskell. We've seen this before, particularly with monads. So we'll add this unit type, which is just written as empty pair of brackets, and it has one value in it, which is also written as an empty pair of brackets. So the empty pair of brackets, this empty unit value, is of type unit, right? That's what this is saying. And we don't need to prove anything in order to show that that's of type unit. It just is. So with the toolbox that we have so far, we've got functions, we've got tuples, and we've got unit types. We can't express a type with exactly 3 values, right? Even if we had booleans, we probably still couldn't do so, because like this traffic light example, we can't come up with equivalent value for red, equivalent value for amber, and equivalent value for green, such that those are the 3 possible values in the type and there are no others. If I represented it as a tuple of 2 bools, then I'd have an extra configuration which I wouldn't know what to do with. So in general, what we want to be able to do here is say, if I have 2 types, I want to express that my type could be one of either of these 2 types, right? So one of multiple alternatives. Our shape example here before had, which we saw before from the very first lecture, we had like rectangles, circles, triangles. These are all different alternatives for the same type shape, right? So we want to combine these things. In Java, we use something like inheritance to do this, but it's very awkward. In C, you'd use a union, right? And in our minimal version of Haskell, we're just going to take one of the possible types that allow us to do this, the either type. So we say, if you remember the either type, hopefully you do, it's either left A or right B, right? Those are the 2 constructors, left and right, and we have, and the type is called either AB. So we've seen this type before, and we're going to build this type into our language, right? It's the only such type that we'll add in. So we have tuples now, we have unit, and we have functions, and we now have also either A, B, right? These sum types, they're called. So then we can express a traffic light, the 3-valued type, red, amber, or green, as this sort of monstrous looking type, which is either it's the left-hand side, which is just unit, or it's the right-hand side, which is either, once again, left unit or right unit. So this gives us a bunch of possible values here. I'll come back to the previous slide. So now our traffic light is expressed this way, and then red is the left unit, okay, and then amber is the right, so we go to the right hand side here, and then the left, and then green is right and then right. So each of these 3 different unit types are expressing the 3 different possibilities that we have, and we combine them together with either. So this is how we can express a 3-valued type using just unit, either. And we also have tuples and functions, but this is all you need for this particular example. So the rules that we have for either types are a little bit interesting. So for the constructors of either, left and right, are probably as you'd expect. If E is of type A, then if I apply left to E, then I get an either AB. If E is of type B, then I apply right to E, I get either of AB. But the rule to eliminate, or the rule to make use of an either type, is a little bit strange. It says if I know, or if I have an expression E, which is of type either A, B, then the way I use an either value is to case match on it, right? To pattern match. And we only have lambdas in our language, we don't have equations, so the only way we can do pattern matching is with a case expression. So we'll build in this type of case expression where we can say case E of left x or right y. And if I have the expression E1 here, then if x is of type A and E1 is shown to be of type P, and y is of type B, then E2 is shown to be of type P, then overall, regardless of which branch this case expression takes, it's going to be of type P. So this looks suspiciously similar to the disjunction elimination rule that we saw before. Okay. So I'm going to add one more type here. And this is just the type which we call void. And it's the type that has no inhabitants. You can't construct a value of this type. You might think that that has no practical use case, but it does have some uses, which I'll go into in a moment. But because you can't construct this empty type, then there is no constructor for it, so there's no introduction rule. But there is an elimination rule that says if E is of type void, then we add this expression absurd E, which doesn't exist in Haskell, but let's just assume that we have some way of doing this, where given an E, we will do something with this value. So what type should this have? So if I have a variable of this type in scope, right? If I have a value E of type void, then this expression cannot be evaluated. I know that it won't be evaluated because it's impossible to have a value of type void. So if there is something in scope of type void, then that means that this expression here will never happen. It will never actually reach this expression at runtime. So that means that we can assign any type we like, which I just called P here, to our expression absurd E. In Haskell, we could just define absurd to be undefined or error. It doesn't matter because we know if there is a value of type void in scope, we will never get to this point. This expression will never be evaluated. So the void type does exist in Haskell, although I think you might have to import a module to get it, but it's there. Now, why would we ever want this type in a practical sense, not just a theoretical one? Well, if you have a function that is not intended to ever return, for example, it's good documentation to make it return void. So for example, if you have an infinitely looping function that just continuously takes input from the user, it would probably be of type A to IO void, right? IO void implies that it's never going to return. Okay, so this is my void type. And now let's just take all of our rules for all of the types that we've introduced so far. We have tuples, functions, the unit type, the empty type, and some types, the either type, right? So we end up with all of these rules. So if we stare at these rules for a little while, we might notice, let's take a look just at the rules for lambda, for example. The rule for lambda introduction, or lambda construction, says that if I have x of type A and E is of type B, then this overall expression is of type A to B. Well, this A in my context and then concluding B, and then overall conclude A arrow B, well, that looks very similar to the rule for implication introduction. And if I look at my function application typing rule, if E1 is of type A implies B, oh sorry, I almost let it slip. If E1 is of type A to B, and E2 is of type A, then E1, E2 is of type B, A arrow B, A, B. That looks like modus ponens. Similarly for our tuples, if I have A and if I have B, then I have A comma B. Well, that's sort of like and, right? So like A and B. If I have A and B, let's say, then that's the same as A. Well, then I conclude A. And similarly, if I have A and B, then I can conclude B. This looks like the rules for conjunction. And as we said before, the either rule here looks like the elimination rule for disjunction. And this looks like the introduction rules for disjunction. And this looks like the elimination rule for false. And this looks like the introduction rule for true. If I get rid of all of the expressions here and just leave the types, then this is exactly the rules of constructive logic. So this is a very strange coincidence. Why did our type system end up looking like logic? If this means that, oh, the slide got cut off there, but it says, if we can construct a program of a certain type, we have also created a proof of the proposition that corresponds to that type. So if I have a program of type either AB to either BA, then I have proven that A or B implies B or A, right? I translate my type into logic, and then the program constitutes a proof of that logical proposition. This is a really deep result. It actually applies universally across all type systems and logics. So types correspond to propositions. So here I translated either to A or B, and tuples to A and B, and functions to implications, right? Programs correspond to proofs. So if I can write a program of a particular type, that's the same thing as proving the proposition associated with that type. And evaluation corresponds to proof simplification, and I'll give an example of that in a moment. So this typed lambda calculus corresponds to constructive logic, right? It doesn't correspond to the classical logic that you might be used to. So there are certain propositions that you can't prove this way, at least not in the language that we described. However, if you add extra features to this language, you get different logics. If we add a feature called continuations, which I will maybe discuss in my next course, COMP3141, if we have time, then you get a notion of a logic that corresponds to classical logic that we're all used to. However, continuations are a fairly uncommon feature in many languages. However, exceptions come close, they're similar. If we add monads to our language, we've seen monads before, then we have what's called modal logic. So some of you may have heard of modal logic. If you do the arts logic courses, I think they talk about that. Linear types, which I've mentioned before, although we've not discussed them in this course, correspond to a logic called linear logic. And region types correspond to a program logic called separation logic, and so on and so on and so on. We have every programming language feature corresponds to some particular logical feature and vice versa. So this means that there's a huge variety of results that have been independently discovered by a logician and a computer scientist, and then years later, sometimes not so long afterwards, depending on which event you're talking about, they discover that these two things are in fact the same. So if I wanted to prove commutativity of something like conjunction, then I could do that by providing a function. If I have, remember, conjunction corresponds to tuples, so if I have a function of type a tuple of A and B to a tuple of B and A, that's the same thing as A and B implies B and A, right? Which is my commutativity of conjunction. To do transitivity of implication, if we write out the type, we get A implies B, right? Implies B implies C, implies A implies C, right? So this is saying if A implies B and B implies C, then A implies C. And this is just function composition, except flipped around. Right? So transitivity of implication is actually proved by function composition, the type. So to summarize all of our translations here, if I want to translate a tuple into logic, I get a conjunction. If I want either, that's a disjunction, and vice versa. Functions are implication, unit is true, void is false. So let's look at now how equational reasoning, that the reasoning that we did on our programs at the very beginning of this course, turns into proof simplification. So suppose I wanted to prove that assuming A and B, that B and A is true. So I've got this proof tree here, right? I show B and A, assuming A and B. So I work my way up. First I use my my AND introduction rule, and that requires me to prove B. Here I use my AND elimination rule, and I get to my assumption A and B. Here I use AND elimination rule, but instead of going A and B here, I decide to write A and A. And then I use my introduction rule, get A, and then I use my AND elimination rule again, and then get to my assumption. So this proof is a bit unnecessarily complicated. So let's make our assumption here, give it a particular name, and we'll call it X. So X is now of type A tuple B, right? So it's a product type, a tuple containing A and B. And so now I've translated my ANDs into tuples here. And if I want to get if I have an A and B, or a tuple of A and B, and I want to get just the B part, then I apply second to X, so I get that. And then similarly here, to get the A out of the tuple, I need to apply first. And then I have a tuple containing first X and first X. Okay? And then second of first X and first X. I could have picked first here, it doesn't matter, but I chose to pick second just for funsies, I guess. And then overall, put these two things together, and I get my overall expression here. So assuming X is of type A and A tuple B, this expression here is of type B tuple A. And we know that if I take the second part of X, right, and the second part of the first part of X and the first part of X, so second of this tuple is going to just be the second part of this tuple, which is first of X. So overall, this is just second X, first X. So if I apply that simplification to the proof, I now end up with this tree, right? So this is easier to show has the right type because it's a smaller expression. So I simplified my program here, and now I translate it back into logic, and I get a much simpler proof of the same proposition. In fact, this is what's called the canonical proof of this proposition. So if we evaluate a program, apply some equational reasoning to our program, we are also simplifying the proofs that correspond to that program. And if we evaluate a program until it reaches what's called its normal form, i.e. the form in which we cannot evaluate it any further, then we get the canonical proof of that program. So this is, in my opinion, a very cool result. And Phil Wadler, who is my colleague at Edinburgh, has released a great entertaining talk about the history of this discovery and some of its implications, and I'll link his talk on the course website. So I encourage you to watch it. It's a lot of fun. He's a great speaker, and yeah, I'm sure you'll enjoy that talk. Okay. So I've mentioned before, we've had dependently typed languages such as Agda and Idris that allow us to remove the distinction between value level and type level languages, which allow us to do a lot of very interesting things with type systems. I'm not going to demonstrate them today. However, that will be the topic of next week's extension video. It's an extension lecture, so it's not assessed, but it's a very interesting topic. Essentially what we're going to be doing is using the Curry-Howard correspondence, which is what this correspondence is called, by the way, to prove a lot of interesting properties. Okay, so this correspondence between programs and proofs does come with a few caveats. As we said before, these proofs are for a constructive logic, and while it is possible to have classical logics work here, normally in a Curry-Howard correspondence setting, we only concern ourselves with the constructive fragment of logic. The other big caveat is that all of the functions that we define here have to be total, right? So we can't have any partial functions, and terminating, which is also actually a non-terminating function is also not total. So total is sufficient, but we'll just, to be clear, they have to terminate and they have to be total. The reason for this is otherwise we would get what's called an inconsistent logic, which lets us prove things that are false. So for example, if I wanted to prove p equals mp and I didn't have this restriction that all my functions should be total and terminating, then I could just say my proof is equal to my proof, right? It's an infinite loop. And this infinite loop is a program that is of type p equals mp. As far as the type checker is concerned, if I put this into Haskell, that would be true. And then similarly, if I did the same thing here, p is not equal to mp, then Haskell would also approve of this type. So the fact that I can prove two contradictory things suggests that my logic is inconsistent. So inconsistent logics are pretty useless because, well, we can prove anything. However, if we restrict ourselves to avoid any non-terminating functions, then we're in the clear. It's safe. So that's the main caveat here. We have to make sure that all of our functions terminate. And that's why I said when we boiled down our language Haskell into this typed lambda calculus, I said that we will be able to express most of the data that we normally have. Most of the data types we would otherwise define. The reason I didn't say all of them is that I didn't include recursive data types here. It is possible to have some limited recursive data types, and they're what's called the inductive data types. And there, recursion corresponds to an inductive proof. And I'll get into more about what that's about in my extension lecture. But in an inductive proof, you need a base case, right? You need to be able to show that it's true for 0 and then it's true for k plus 1. So that inductive proof corresponds to a well-founded ordering which ensures that our proof or our program terminates, right? So even in the inductive proof examples, they don't go on forever, right? They eventually stop. So these non-terminating programs are bad, and so we don't allow infinite recursion or infinite loops when we're talking about the Curry-Howard correspondence. Okay, so the next thing I want to talk about is a little bit more about these various different types that we have. So I said that these building blocks of sums, products, so either and tuples, sums and products, unit and empty are enough to build up like most of our data types. Now what we're going to do is see how to do that a bit more explicitly. So we can come up with a bunch of sort of equivalence laws about types. We can say, for example, if I have either of either A, B, and C, then I can write, I can sort of say that that's equivalent in some sense to either A, either B, C. And if I translate this into logic using Curry-Howard, I can see that. So for example, A or B or C is the same thing as A or B or C, right? It's the associativity rule for or. So these are logically equivalent. Similarly here, if I have false or A, that's the same thing as A, right? And similarly, also, like, you can imagine that either empty type or a value of type A is the same thing as just the value of type A in some sense. Commutativity, I can swap the left and right of the either and it still works, right? And similarly, these are logically equivalent. A or B is the same thing as B or A. And if I have tuples, well, firstly, we have tuples are also associative in some sense, right? A tuple of A, B, and C is equivalent in some sense to A and then B and C. If I have a unit type and an A, then that has the same amount of information as just an A. And equivalently, true and A is the same thing as just A. We can flip the arguments of a tuple, and we've still got the same amount of information here. And we can also distribute tuples over either, and we don't lose anything by doing that translation either. Similarly, if I have 0 and A, if I have false and A, that's the same thing as false, right? Or similarly, if I have a value of the empty type and an A, then I can just as easily, I can't construct a value of the empty type, and I therefore can't construct a value of the type void tuple A, because I'd still need to construct a value of the empty type in order to do that. So this is equivalent, has the same amount of information as void. So I wasn't very clear about what this equivalent symbol means, right? It isn't just logical equivalence, right? If we translate all of these into logic, then these are all equivalent logical statements. But another example of an equivalent logical statement is either let's go either unit, which is true or true, right? That's equivalent to just unit. But either unit has two values. It has left unit and right unit, whereas just unit by itself has only one value. So if I translated from either unit into unit, I would lose some information. So this equivalence is actually stronger than just logical equivalence. Logical equivalence is an equivalence here, but this is even stronger. It distinguishes more things. All of these equivalences say that the amount of information in either of these types is the same. In other words, the number of different values that could it be of this type is the same on both sides. How many possible tuples are there of unit and A? Well, it's the same number as however many values there are in A, right? Similarly here, how many values are there in a tuple of void and A? Well, it's in order to construct a tuple, I need to construct a value of type void, and there are 0 inhabitants of type void, so there's 0 inhabitants overall. So let's try and figure out the size of each of these types, the cardinality, if you will, of each of the types. We've got ourselves some tuples, A and B. This is the size of this. How many possible values are of this type? Well, let's look at an example. If I have unit and bool, right, that the size of this is going to be the size of unit, like I could have unit true and unit false, right? So there's two possible values here. And if I have bool, the size of this is, well, I have true, true, false, true, and then the same with false on the other side, so we have a total of 4. So this looks like the size of A and B in a tuple is the size of A times the size of B. This makes sense because these tuples are called product types. Similarly, if I have the size of either A and B, that's a sum type, and as we'd expect. Therefore, its size is size of A plus the size of B. The size of unit is 1. The size of void is 0. And the size of functions, we haven't discussed this much, but if you think about the size of a function, it's actually the size of the codomain to the power of the size of the domain. And I can give you the intuition as to why that is. If you want, just ask me on Piazza. Don't really have time to talk about it right now. I don't think, anyway. Yeah, I should probably keep going. But anyway, this information, these formulas here, this one, this one, this one, and this one, as well as, I guess, this one, is enough to give us the size of any particular type that we want. And if we look back at our equivalence rules here, all of these have the same size, right? And so what I'm saying by this equivalence is we're not losing any information if we translate from one type to the other. They have the same number of possible values, which means that we can construct a mapping from every value of one type to every value of the other type, such that we don't lose anything, right? It's injective and surjective. In other words, this has a bijection between the two types. For every value of one, I can provide a unique value of the other, okay? And that's what this sign means. That's what this equivalence means. And what this equivalence is called is type isomorphism, okay? So two types are isomorphic if there exists a bijection between them. So for each value in A, we can find a unique value in B, and vice versa. So why do we care about type isomorphism? Well, we can use those laws that I described in the previous slide to simplify our type definitions. So if I look at switch here, I'll go back to the board and write it out. I have data switch equals on, and it's got a name and an int. So this is like an electrical switch or something, so it could be either on or off, and the switch has a name, and it also has like some current going through it, the amount of current going through it if it's on, so that's the integer, let's say. Now if I try and convert this data type into my sums and products and everything, then this will be the product of a name and an integer, right? It's a tuple of a name and an integer on one hand, or it could be, so not plus, should write either. So it's either a name or an integer, or it's just a name, right? So now left has taken the role of on, and right has taken the role of off. But yeah, we don't want to use this explicit data type, so we converted it into this. So now, if I go back to my slides briefly, we have this distributivity law here that says that if you have, oh wait, let's not use that one yet. Let's first use the rule that says A is the same thing as unit and A, okay? So what I'm going to do is take that and change this to either name int is the same thing as unit and name. And what did I call that rule? Identity for tuple. So tuple identity, right? So that's equivalent in some sense. And then let's flip this around. So we get either name int name unit. This is tuple is commutative. And now we can see that we have this common factor, so to speak, of two names, and we can factor that out using the distributivity law that we saw before. So we get name on the outside, and then either int or unit. Now, if we think about our maybe type, maybe A is just A or nothing. This is effectively the same thing as either it's A or it's unit, right? In the nothing case, we don't have any extra information, so it's either left A, which is the just case, or it's right unit, which is the nothing case. So this translation means that either int unit here is the same thing, if I take that translation and go backwards, as name maybe int. So what I did here is take my type definition and convert it into another type, and I know that this type is equivalent to this original type. And in order to convert a value of this type switch, to write a function f of type switch to name maybe int, it suffices to take a function that converts between each of these steps and compose each of these functions together. Okay? So this is actually quite a nice way to reason about type transformations, and it is very useful when it comes to refactoring. So in particular, if I look at my original type here, we may wish to access the name of a switch without caring if it's on or off. Right? We don't want to have to pattern match on the switch to check if it's on or off when we only want the name and there's a name in either case, right? So we should be able to just extract it. If we do this simplification, then we don't have to do that pattern matching anymore, which is a bit more efficient. So we've improved efficiency by using this reasoning about types to refactor our program. So that's one use case for this type isomorphism. Another use case is generic programming. So the word generic programming is unfortunately heavily overloaded. There's many different notions of what's called generic programming, but in functional programming and in programming languages theory, we generally refer to generic programming as ways to define algorithms that work on any data structure. So what we're talking about here is things like deriving. So if you imagine show or EQ or ORD or many other type classes in Haskell, in order to get an instance for them for your particular data type, you can just write deriving and then give a name of that type. So how does this actually work? Well, what it's doing is it translates this data type definition that you wrote into sums and products. So essentially either and product and tuples and all of these basic building blocks. It translates whatever definition you provided into these basic building blocks, and the algorithm, say show or ORD or EQ, is defined on those basic building blocks instead of on the type that you normally define. So it translates your type into the basic building blocks and then defines the algorithm on those. This allows you to write an algorithm that works on any data type, provided it's defined for sums and defined for products and defined for functions and defined for all of the basic ingredients. And that's how we get our deriving instances. And there's libraries in Haskell, specifically GHC supports this generics programming library that essentially allows you to do this for your own type classes as well. A famous example is JSON. So hopefully many of you have heard of JSON. It's basically a way of representing data in a JavaScript-friendly way. And this JSON, there's JSON deserializing and serializing type classes in a special library. This library isn't built into GHC or anything, but it allows you to derive conversions of your data types into JSON or from JSON, right? And the way it does this is with generic programming. So if you're interested to learning more, please ask me and I'll provide you with some links. But essentially, it's a very cool way to define algorithms that work regardless of the specific data structure that we're working with. So the other thing I'll mention about this before I move on is I called these sums and products, and we can actually rewrite our expressions here, and it makes the reasoning that I just did very intuitive. If I write these as plus and times instead of either and tuple, I get name times int plus name, right? And then this one below is name times int plus 1 times name, right? We know that that's the same as name times int plus name times 1. And that's the same as name times int plus 1. And yeah, and so if you can see now that all of the steps that I just did, while it looked like I was applying a whole pile of new rules, they were all just the same rules as what we have with arithmetic. If I go back to my list of rules that I had before, if we consider either here to be plus, right, a sum type, right? So if we consider this to be plus, we know a plus b plus c is the same regardless of where I put the brackets. Similarly, 0 plus a is the same as a plus b is b plus a. This is just addition, right? And for tuples, it's just multiplication. A times b times c is the same as a times b times c, regardless of where I put the brackets. 1 times a is a times b is b times a. And then we can distribute multiplication over addition. A times b plus c is a times b plus a times c. And 0 times a is 0, right? So the coolest thing here is that the reasoning that we're doing about types is actually just the same as arithmetic. There's nothing different. And that's what we mean by commutative semiring. Okay. All right, so the last topic that I want to talk about with regards to the theory of types is polymorphism. So all of the types that we were looking at so far were not polymorphic types. They were just like concrete types. We were just talking about like switch here, for example, takes no type parameters. When we dealt with maybe, we applied it to an argument int, right? So we're using int spools, everything that is like constant built-in types or whatever. Now we're going to talk about polymorphic types. So if we look at the function first, it takes in a tuple of a and b and returns an a. And what these a and b's are is up to the caller, right? The caller decides whatever a and b should be. So we can actually write this in Haskell if you turn on an extension as for all ab dot a and b to a. So we can use this upside down for all if we want to make this for all look a little bit prettier. Essentially, we're just saying that for any type A and any type B, this function will take in a tuple of those two types and return a value of the first type. This notion of quantifying over types with this for all is called parametric polymorphism, or just polymorphism. Some languages call it generics, specifically Java, which is a terrible name because generics refers to this stuff, not to this stuff. But in any event, this is very irritating. When we say polymorphism, we mean this, and when we say generics, we mean this. Whereas in Java, when they say polymorphism, they mean something completely different, and when they say generics, they mean polymorphism. So please just forget all the object-oriented programming terminology that you have ever learnt because it's all wrong. So what's the analog of this for all types thing in logic? Well, we've seen this for all symbol before, or at least I hope you have, whenever you did discrete maths. It essentially corresponds to for all in logic, right? However, it's not exactly the same thing as for all in logic. Specifically, it's not the same thing as the for all in first order logic. In first order logic, a common way of using for all would be to quantify over some individuals, say numbers. We'd say something like for all x plus 1 is bigger than x, right? That's a first order logic proposition, right? So all of the propositions we were dealing with before we talked about polymorphism were just propositional logic, but now we're dealing with first order logic, so we're going to add quantifiers. So if I say for all x plus 1 is greater than x, that's a first order logic proposition. But if I take the type of first here with the for all, and I convert that into logic, I get something like this. For all a, for all b, a and b implies, it should be a and b implies a, right, for first, right? A and b implies a. So these for alls here are not quantifying over numbers or individuals of any particular set. They're talking about propositions themselves, right? This is saying for any proposition A and for any proposition B, A and B implies B and A, right? So our quantifiers here are ranging over propositions, not numbers or individuals of some set. And this is the difference between what's called second order logic, where we quantify over propositions, and first order logic, where we quantify over individuals. We do, however, have a way to quantify over first order logic things as well, and that's data kinds. We've seen data kinds already, right? We can talk about values in the type level of kind int, right? Or of kind nat, or other things like that. And when we do that, what we're doing is this kind of quantification. You're saying for all types of kind int, x plus 1 is greater than x is actually a valid thing, you could say. But that kind of data kinds polymorphism is much less common than normal type polymorphism, which is second order logic, not first order logic. So this just goes to show that when we add polymorphism to our language, we still have a Curry-Howard correspondence version of that in logic, right? Everything corresponds to something in logic. Okay. The next thing I want to talk about is generality of types. So if I have a function of, and I know Curtis talked a bit about this actually very early on in the course, so maybe you can recall that. If I have a function of type integer to integer, or if I need one, right? Suppose I must provide a function of type integer to integer to my program. Then if I have a function of type for all a to a, right, say identity, I can pass that into my program that needs int to int, and it will be fine with that because I can just take that a and instantiate that a to be int, and then I've got myself the type that I want. But if my program required a function of type for all a to a, and I gave it a function of type int to int, that's not good enough. The function that the program expects must work on any type a, not just on integers. So this means that we have an ordering on types as to how general they are. How many situations could I use them in? We say a type A is more general than a type B if I could instantiate some of these variables. I could replace some of these variables, like lowercase a and lowercase b, with concrete types, and then I would get the type B, right? So here I can replace the a with int, and I get the type int to int, which means that for all a to a is more general than int to int. And more generally, I can say this: int to int is less general than for all z to z, which is just say a to a, right? I could instantiate the z to be int here, and I would get this type. And this is in turn less general than for all x, for all y, x to y. I could replace both x and y with z, and I would get this type. So This is more general. And then here, this type is less general. Then just for all a, I could replace a with x arrow y, and I would get this type. So this is the most general type in this list, and this is the least general type. So let's think about how many possible implementations of a certain function there are. How many functions are there that implement int to int? Well, it sounds like there will be a lot. I did show you the answer before, but maybe we do have time to explain it after all. So where is my pen? I appear to have misplaced it. Oh, there it is. So, because int is a big type, let's first deal with booleans. If I have a function of type bool to bool, how many possible implementations of this function are there? Well, there's the function that always returns true, which in Haskell you could write as const true. There's the function that always returns false, which in Haskell we could write as const false. There's the identity function, which just returns its input, and there's not, right, which flips it from true to false and false to true. If I have the function type for all a to a, well, I can't do this because this always returns true, and true isn't necessarily the same type as a. So this one gets ruled out. Same with this one. Not also gets ruled out because I don't know that a is a boolean. So the only one of these that survives is identity. And in fact, I can't write any other total terminating function that implements this type here except identity. It's the only implementation. So as we said before, the number of inhabitants of a function a to b is the size of the codomain to the power of the size of the domain. So there's 4 functions, which is what we expect. And here, when we go to a more general type, right, this is a more general type, we actually only have 1 inhabitant. So the more general our type gets, the less implementations we have. We're actually restricting the number of possible implementations as we go to a more and more general type. If I go to the next most general type for all a arrow b, for all a arrow b, well, there's no way I can write, there's no functions here. This type is not implementable, because what this is saying is, if any proposition A and any proposition B, A implies B. So that means true implies false, for example. That's nonsense, right? There's no way I can define a function of this type. So there's 0. So once we go more general, we get to 0. And even more general than that, for all AA, this is saying for all propositions A is true, right? That's saying every proposition is true, including false. That's clearly rubbish. So there's also 0 total terminating functions of that type. So the more general you get, the less functions you have. Okay, that's the intuition I want you to think about. So the polymorphic type signatures that we have constrain the number of implementations that we can have. This has huge practical implications. It means that the number of possible ways I could implement a function go down if I have a more general type signature. And the more general my type signature is, the less mistakes I could possibly make when implementing that function. So there's a notion of what's called parametricity. If I take a look at a parametric function type, let's take a look at, say, go back to the board again. Head is of type for all A, list of A to A, right? This is our type. And there's really I could not implement head by saying, okay, head takes in a list and returns 2, right? This is not possible because 2 and A are not known to be equal, right? Or int and A, rather. Int and A are not known to be equal. So we can't just return some arbitrary value. We have to return something that is known to be of type A. And the only values that I have in head that are known to be of type A are values inside the list. So I have to return one of the values inside my list. So what this is saying is that the output of head must be in the input list. Right? And I can conclude that just by looking at the polymorphic type signature. If I gave head a less general type, suppose I was only dealing with lists of integers, then I could have a function like this, head of a list equals 7, and this would be type correct. It's not actually correct, obviously. We don't want to always return 7 regardless of what the list is. But this incorrect function, the type checker said that's fine, but if I give it a more general type, the type checker will rule it out. So the more general my type is, the less wrong my functions can be. There's also a mechanical way to come up with the theorems that these type systems provide us. So let's look at some examples. So the principle here is called parametricity. And what it says is we cannot depend on the values of a particular type that is parametric here. So for example, in head, we have this type A. We cannot depend on the values of that type A because we don't know what A is. There's no way of interacting with those values. There's no way of looking at them and doing anything about them. So the behavior of head, for example, is not affected by any of those values. So no matter what values are inside my list, it doesn't matter what specific values there are inside because I know that from the type signature, head will never look at those values. The only thing head can do is take one of the elements out of the list and return it. And we want it to be the first one. Okay, so so the way we define this theorem more formally is if I run some arbitrary function on all of my values of type A, which is my polymorphic quantified type, so if I run my function on all of the input values of type A, and then call the function that I'm looking at, and then that will be the same as if I had called my function and then run that arbitrary transformation on all of the output values of type A. So as an example, suppose I have this function foo. I don't know anything about what it does, and it takes in a list of A's and returns a list of A's. So as we saw before with head, this output list of A's must consist entirely of elements that are taken from the input list of A's. And there's nothing this function can do that would change its behavior based on which values of type A that are in there, right? So the theorem that we get from this formal definition is if I run some arbitrary transformation f on all of my input values to foo and then call foo, that's the same thing as if I had called foo and then run my transformation on all of my output values of type A. So the theorem is if I call foo and then run the transformation on all of its outputs, that's the same as running my transformation on all the inputs and then calling foo, right? And so this is the formal property that is guaranteed for us by the type system. Okay, let's look at head. So once again, going back to head, what's the parametricity theorem that we'd get here? Well, it says if I call head and I run some arbitrary transformation f on all of my inputs, right? That's the same thing as running my transformation f on all outputs of type A, and there's only one, so it's just going to be f, not map f, of head inputs. So because I can change any of my inputs in type F with the function f, that means that head is not allowed in any way to depend on which values are in the list inputs, right? It can't say if there's a 3 in the list, then return the 7th element, for example, because that requires it to know what the type A is. So this is the parametricity theorem that we get for head. Okay. Next, let's look at something a bit more complicated. We have plus plus here. So plus plus is of type for all A, list of A to list of A to list of A. And once again, it cannot depend on any input of type A. So if I have my special transformation f and I apply it to all of my inputs of type A, so I need to use map to get at those. So let's call it x's and map f. Oops, I'll write the function in a different color. If I write my special transformation on my input values of type A, if I append those two, that's the same as running my transformation on the result of append, right? These are equivalent. Right? And let's do another example, concat. So this takes a list of lists and just flattens it down one level. So we have concat list of A to a list of A. So first I need to run my function f on all of my inputs of type A. To do that, I need to not just map f, but map f. And the reason I do twice is because I need to get into 2 layers of lists, right? And if I do that and then concat my results, then that's the same as if I had just run my transformation, and I only need to run it once here because I've only got one list here of concat x's. Okay? So it's always basically run a transformation on all your inputs of type A and state the expression for that, and then run transformation on all your outputs of type A and write the expression for that, and those two expressions are going to be equal when you have a polymorphic type for all A, right? Okay. Now this last one's very tricky. We have filter here, and the reason it's tricky is filtered has a predicate here that takes in a value of type A. So let's write it out. Hold on, my mouse isn't cooperating. Here we go. So filter takes in a predicate, A to bool, list of A to list of A. So we want to run our transformation f on all of our inputs, map f on our inputs, And then we want to give that to filter. And we'll call our predicate P. Okay. And now we want to run F on our outputs. But the predicate that we're going to give it is not just P, because P may depend on what A is, right? P is not necessarily polymorphic on A. In fact, it almost certainly isn't. So for example, I can call filter with greater than 2, and that greater than 2 is assuming that my list has a list of integers. The only function that has to be kept, that cannot depend on what the type A is filter itself, not any of its arguments. So we have to be careful here. Here we ran F on all of our inputs before they were passed into our argument function P, but here we run F afterwards. So the actual equivalent predicate here is P composed with F, right? But that's a very tricky parametricity theorem, but you can still get there. This is the theorem that the type system automatically proves for us. Okay. So this means that, and some of these theorems are non-trivial, right? To prove these theorems yourself would require presumably some induction, a fair bit of work. But now, because of our type system's generality, we have just proven these without doing anything, right? Just by writing this generic type, that the type system can automatically determine that this theorem holds, right? We don't need to do anything else. And that's why I was saying way back when we talked about functor, that if you have a functor implementation that satisfies the identity law, then it also satisfies the composition law. Because if you take the parametricity theorem of map, you'll get very close to the composition law anyway. Okay. So, you might be worried now because it can be tricky to come up with these parametricity theorems yourself. The paper Theorems for Free, which is also written by Phil Wadler, who I'll link the talk to about Kari Howard in the lecture notes, is a very nice read, and it describes how we can actually mechanically, automatically determine what the free theorems are for any particular function. And so that means that I'll never ask you to come up with the theorem yourself, because we don't need to. A computer can do this for us. So let's look at a computer doing this for us. Here I am on an IRC channel. If you don't know, IRC is like old people's Slack. Essentially, it's a chat room service that's been around for years, longer than I've been alive. And this is the Freenode IRC server, where there is the Haskell IRC channel with a lot of very helpful people. So if you're having trouble with Haskell, you can always ask them for help. And as you can see here, I've asked LambdaBot in a private message to give me the free theorems that I get for head. And it's given me the parametricity theorem for head. I can similarly ask it, well, what's the free theorems for a function of type list of A to list of A to list of A, which is the append type? Oh, I've got to give the function a name, so I'll call it foo. And it says, well, if you run map f on foo of x's, that's the same thing as foo of map x x's composed with map f, right? Yeah. And if you want to see that a bit more clearly, if I write it as plus plus, does it do it better? No, it doesn't. Okay, it doesn't like that. But if I expand the composition here to give it an explicit argument, then we get the same theorem that we had for append. If I do another example, just list of A to list of A, bar, then it gives me my familiar map theorem there. And if I ask for the free theorem for filter, it already knows hopefully what filter is, yep, and there it is, right? So we can just ask LambdaBot if we don't know what the theorems are, and it will be able to tell us very easily. Okay, I think there is LambdaBot implementations on many other Haskell chat servers. It's just the IRC channel is the only one I know. Okay, so that concludes the entirety of the accessible course content for this course. On Wednesday, Curtis will continue to help you practice some of the Carrie Howard concepts and a few other concepts that I discussed in this lecture. And next week, we will have an extension lecture where I will talk about AGDA and IDRIS and dependently typed programming languages and proof systems as programming languages and all sorts of complicated stuff. It's just for interest, though. It's not for educational. It's not for, well, it is educational, but it's not for accessible content. And on Wednesday, Curtis will do a revision lecture, which will include discussions of the sample exam that I will post probably in a day or two. I still have to make it work. UNSW cancelled our Inspira trial, which means that I had to at the last minute create my own exam platform for doing exams online, and I have yet to put the sample exam into that platform. Once I do that, I'll make it available to all of you, so you'll be able to actually do the exam as if you were doing it like in real life, and we'll also have solutions available for you to see. And yes, so I think that's all I wanted to mention. Assignment 2 is still out. There's no exercise for this week. There is a quiz. And yeah. Thank you very much for all of your attention during this course. I hope you had fun. I know it can be stressful and there's a fair bit of work, but good luck with the rest of your studies. If you're doing COMP3141 next term, I will probably be around for the first 6 weeks or so. But then after that, I'll be leaving. I'm going to the United Kingdom to start my job at the University of Edinburgh. So it's been very nice teaching all of you. And maybe in the future, if you consider an academic career and you don't mind moving to Scotland, get in touch with me and we can talk about if you want to do a PhD or something like that. Let me know. Maybe there's something I can find for you. Otherwise, if you are looking for more interesting topics to cover, more interesting courses to do in this area, I highly recommend the following. There's quite a list. So we have COMP3141 is probably the closest related course to this one, and I'm teaching the first few weeks of that next term. And it's about programming languages and formal semantics of programming languages. It's quite a bit of math, but it's a rewarding course and it's highly reviewed by a lot of people. I also recommend COMP4161, Advanced Verification. If you enjoyed the proof part earlier on in the course, and you enjoyed the lambda calculus and logic parts of this lecture, then you will very much like COMP4161, which is about using an interactive theorem prover called Isabelle to prove theorems about software, and also about like general mathematical theorems in general. It's quite an advanced course, but I think it's quite rewarding and it's very useful if you plan on being a computer scientist to learn a theorem prover. So I would say COMP4161 is a very valuable course. There's also some other courses that are near to my heart, but not so closely related. COMP3151, Foundations of Concurrency, which I am lecturing at the moment. If it runs again next year or in future, I highly recommend you take it. I don't know if it will be any different next year, but at least when I did it and when I taught it, I think it was a good course. Similarly with COMP3153, Algorithmic Verification. This is about algorithms to automatically prove properties about programs, and it's about static analysis and things like that. That course was, in my opinion, quite fun to teach, but as I'm leaving, I don't know who will be taking that over, and I don't know what it'll be like next time it runs, if ever. But if it does run, I recommend it as well. I also recommend the course COMP6752, Modeling Concurrent Systems, which is also taking a very mathematical approach to concurrent systems, even more mathematical than this course. I found it a very rewarding course to do, and I highly recommend that. Okay, and I think that's all of the main things that I wanted to recommend. I do recommend that you do certain other theoretical courses that are not so closely related, like algorithms. I think you all have to do algorithms these days. And COMP3141, Theory of Computation, is also a very valuable course to do to round out your theoretical knowledge. Yeah. Apart from that, good luck with your exams and good luck with everything. And I may or may not see you around next term. Thank you.